Welcome back to Chem Talk, everyone, where we try to make chemistry, actually interesting.
Yeah.
So today we're doing a deep dive into
Okay.
6-1 Mendeleev's periodic table,
Nice.
which sounds maybe not super exciting, but it's
Right.
like figuring out this giant puzzle
Yeah.
that unlocks like all the secrets of matter.
It really is a fascinating story. Back in 1869,
Okay.
Dmitri Mendeleev was facing a challenge.
Okay.
There were about 60 known elements
Wow.
at the time, and nobody had a good system for organizing them.
So it's just like chaos.
Yeah, it was like having this jumbled deck of cards, and you had no idea what the rules of the game even were.
Okay, so he had all these elements, each with their own unique properties.
Right.
So where did he even begin?
Well, like any good scientist, he starts with what he knows.
Yeah.
He knew that elements had different atomic masses.
Right.
Which basically means how much an atom weighs.
Okay.
So he decides, I'm going to arrange these in order of increasing atomic mass, hoping to find some kind of pattern.
Interesting.
And you know what he did?
Wait, so just putting them in weight order
Yeah.
revealed something deeper? Like what kind of pattern are we talking about?
So he noticed that certain chemical properties
Okay.
started repeating at regular intervals.
Uh-huh.
For example, lithium, sodium, potassium
Okay.
all reacted violently with water.
Interesting.
And they have different atomic masses.
Right.
And fluorine, chlorine, and bromine, also with different atomic masses,
Uh-huh.
all had similar reactive properties.
So it's like not just random. There's a rhythm to it,
Exactly.
like a hidden code.
Exactly.
Yeah.
That's the beauty of the periodic table.
Okay.
It's not just a random chart.
Yeah.
It's a reflection of a fundamental order in the universe.
Wow.
And Mendeleev was the first one to see it.
That's pretty cool.
But here's where things get really interesting.
Okay.
He found gaps in his table,
Oh.
places where elements should be
Huh?
based on the repeating pattern, but weren't discovered yet.
Hold on. So he's basically predicting the existence of elements that nobody had ever seen before.
That's exactly what he's doing.
That's pretty bold.
It was incredibly bold,
Yeah.
and a lot of people in the scientific community were skeptical.
Oh,
But
yeah.
Mendeleev not only predicted their existence,
Uh-huh.
he went a step further.
Okay.
He predicted their properties.
Wow.
He's like, okay, there's an element missing here.
Yeah.
And based on where it falls in the table,
Mhm.
I bet it will be a silvery metal, have this melting point and react in this way.
Wow.
And years later, these missing elements, like gallium and germanium, were discovered,
Yeah.
and their properties matched his predictions almost perfectly.
So he was right.
He was right.
He was right.
It's amazing.
Wow, that's like predicting the stats of a new character in a video game before it's even released.
I like that analogy.
Yeah.
Yeah.
Talk about being ahead of the curve.
Yeah.
But wasn't there something bit off with Mendeleev's table? Like, I remember something about swapping elements or something.
You're thinking about tellurium and iodine
Okay.
based purely on atomic mass?
Yeah.
Tellurium should come after iodine on the periodic table.
Okay.
It's slightly heavier.
Okay, so what was the issue?
So, Mendeleev,
Yeah.
trusting his instincts
Yeah.
and his careful observations,
Okay.
did something that seemed to break his own rules.
Oh.
He swapped them.
Really?
He placed tellurium before iodine,
Huh.
even though it seemed to defy the order of atomic masses.
So he prioritized the similarities in their properties over this small difference in their weight.
Exactly.
Okay, but how did he know he was right to do that?
Well,
Was it just a lucky guess?
no, not at all.
Okay.
He was working with limited information,
Yeah.
but he recognized that iodine behaved far more similarly to chlorine
Uh-huh.
and bromine,
Okay.
all elements grouped together
Right.
in a vertical column on his table. And tellurium's properties lined up more with elements like oxygen, sulfur, and selenium, which
Uh-huh.
also shared a column.
Gotcha.
It was a testament to his deep understanding of the elements and their behavior.
So what we're seeing here is that while atomic mass was a helpful starting point,
Yeah,
it wasn't the whole story.
right.
There was something else at play,
Yeah,
some deeper principle governing the arrangement of the elements.
exactly. And that's where our story takes an exciting turn.
Ooh, I like exciting turns.
But to unravel that mystery,
Yeah.
we need to introduce a new player in our game of elements.
Okay, let's do it.
Mendeleev's table was revolutionary, But, like you said, some puzzles remained, like the tellurium-iodine swap.
Right.
So it took another brilliant mind
Okay.
to kind of crack the code further.
Okay.
Enter Henry Moseley,
Okay.
a physicist working with a then cutting-edge technology, X-rays.
Okay, X-rays. So now we're getting fancy.
I know, right?
Something out of a superhero comic book.
A little bit.
But how did this help with the periodic table?
So Moseley was firing X-rays at different elements and observing the patterns they created.
Interesting.
Imagine like shining the special light on each element that reveals its unique fingerprint.
So each element reacted to the X-rays differently.
Exactly.
Okay, and what did these fingerprints tell him?
So he discovered a direct link
Okay.
between the pattern of X-rays, an element emitted, and a fundamental property we now call the atomic number.
Okay.
And it turns out this wasn't just some random number.
Right.
It represented something crucial
Right.
about the atom's structure,
Yeah.
the number of protons in its nucleus.
Right. Protons, those positively charged particles hanging out in the center of an atom.
Exactly.
Okay. But how did this solve, like, the periodic table mystery?
So arranging the elements by increasing atomic number
Okay.
cleared up those like nagging inconsistencies that Mendeleev had encountered. It beautifully explained why he was right. To swap tellurium and iodine.
Okay.
Tellurium, despite being slightly heavier,
Yeah.
has 52 protons,
Uh-huh.
while iodine has 53,
Okay.
perfectly justifying their placement on the table.
So atomic number became like the ultimate sorting hat for the elements.
Yeah, I like that.
Yes.
That's a good one.
Mendeleev's intuition about properties was spot on,
Yeah,
but it was Moseley's work that gave us the underlying reason why.
exactly.
Okay, I'm starting to see how this table isn't just like memorizing a bunch of elements.
Yeah.
It's like a map, a blueprint of how matter is organized at the most fundamental level.
You got it.
Yeah.
And this leads us to the modern periodic law,
Okay.
which states that when elements are arranged by increasing atomic number, there is a periodic repetition
Okay.
of their chemical and physical properties.
Okay, periodic repetition. That sounds familiar,
Yeah.
like the repeating patterns Mendeleev noticed.
Exactly.
But now we're saying it's tied to this atomic number, the number of protons. But why does the number of protons dictate how an element behaves?
That's where things get even more interesting.
Ooh, I like where this is going.
The answer lies in how electrons are arranged around an atom's nucleus.
Yeah?
It's like a very delicate dance with very specific rules. Elements in the same vertical column,
Okay.
called a group,
Right.
share similar properties
Okay, yeah.
because they have the same number of valence electrons.
Valence electron.
Yes, these are the electrons in the outermost shell of an atom,
Okay.
the ones that are responsible for bonding with other atoms.
So it's like each group, each column on the table is a club, and the number of valence electrons is your membership card
Yeah, I like that.
that determines who you hang out with, who you react with.
Exactly.
Okay, but how does the number of protons way down in the nucleus
Right.
affect these electrons way out in the shell?
Because protons with their positive charge
Yeah.
are what attract and hold those negatively charged electrons in place.
Okay.
The more protons an atom has, the stronger its pull on the electrons.
Okay.
And this determines the energy levels of those electrons,
Mhm.
how they're arranged in shells, and ultimately how likely they are to interact with other atoms.
So it's like a cosmic game of tug of war,
Yeah,
and the number of protons sets the rules.
I like that a lot.
Okay, so we've gone from like arranging cards by weight
Yeah,
to like X-ray fingerprints.
right.
It's amazing how much we've learned about the periodic table,
Yeah.
but I gotta admit, it's a lot to keep straight.
Yeah,
Can we like hit the rewind button and
Yeah.
just summarize the key points?
absolutely. It's like putting together a complex puzzle. Sometimes you need to step back and see the whole picture.
Yeah.
What stands out to you as the most important pieces we've discussed?
Well, first, Mendeleev's just sheer brilliance in organizing the elements based on atomic mass.
Yes.
And then like having the audacity to predict those undiscovered elements.
Right.
It's like he was playing this cosmic game of connect the dots. And he knew there were missing pieces out there waiting to be found.
Yeah, and then building on that,
Right.
Moseley's discovery of the atomic number as the true organizing principle.
Yeah.
He provided that missing piece of the puzzle that explained why Mendeleev's arrangement works so well.
Right. Like finding the instruction manual
It's pages.
after trying to build something by trial and error.
Yeah,
And
exactly.
finally, the modern periodic law,
Right.
which explains those repeating patterns of properties based on atomic number
Mm-hmm.
and, crucially, how those electrons are arranged.
Yeah. Yeah.
It's like the rule book that governs the entire game of chemistry,
Right.
dictating how elements interact and form the compounds that make up our world.
Exactly. You got it.
Wow.
Understanding these concepts is like having a superpower in chemistry.
Okay.
It allows you to not just memorize the periodic table,
Right.
but to truly comprehend it, to predict how elements will behave, and even design new materials with specific properties.
So it's not just about memorizing a chart. It's about understanding this like elegant underlying structure
Yeah.
that makes the periodic table such a powerful tool
Absolutely.
for scientists and like
Yeah.
anyone who's curious about the building blocks of our universe.
Yeah.
And on that note, a big shout out to Mrs. Williamson's class
Awesome.
for joining us on this deep dive into the periodic table.
Yes.
Keep exploring, keep asking questions, and remember, chemistry is all around you.